Hi everyone, so for my project I decided to talk about the James Webb Space Telescope Sun Shield. In my opinion, it is a very impressive feat of engineering and it highlights a lot of the concepts that we've learned in material science, so I'm very excited to share this with you today. So we'll briefly discuss just what the telescope is and then we'll go over some of the materials that were used in creating the sun shield, such as Kaplan and aluminium, and then we'll talk about the process of doping silicon and why it was used in the design. This is a picture of the telescope in the background. That lower half is a sun shield, which will be the focus of today's presentation. So the JWST was designed by NASA to observe deep space through infrared radiation, and it has accomplished quite a bit since its launch in 2021. It has been studying different stages of history, such as the first luminous glows after the Big Bang to the evolution of our very own solar system. So there were quite a few design specifications that needed to be met when they were designing the telescope. So for example, it needed to operate at very low temperatures so the sensitive instruments would be overwhelmed by its own IR, and it would need to block the light and the heat from the sun, earth, and moon for the same reason, or else the research wouldn't really get very far if the only emissions it was picking up were those. And so that's why they designed the sun shield. So the sun shield is pretty cool in my opinion. It's made out of Kapton coated with aluminium, and the two hottest layers are also coated with doped silicon, and we'll definitely speak more about that in the coming slides. Kapton is a very thermally stable material, and how the sun shield works is that the heat radiates from between the layers and the vacuum between that space acts as a good insulator. And this image gives you like a little rundown of how it works, and I'll just pause a little bit so you can see that. This is an image of the 3D model that I created. I used Maya from the Autodesk suite, so they're like the same place that has like Tinkercad and AutoCAD and like all of that. And it's very dark because I struggled a little bit, but I had friends that do architecture, so I had quite a bit of help. Next, we're going to talk about Kapton. Kapton is a polyamide film developed by DuPont in the 1960s, I believe. This is a picture of the chemical structure. It has many unique properties that makes it very attractive in engineering design, and it is thermally stable. It can withstand temperatures greater than 500 degrees Celsius, and it is very chemically resistant. Kapton's unique thermal, chemical, mechanical, and electrical properties make it resistant to extreme conditions. It's really no wonder why NASA engineers decided to use this material, because it's like very obviously fit to withstand a harsh environment like space. Over here we have a few properties of Kapton and how they fare when they are exposed to radiation. So for example, the tensile strength is 207 megapascals, but over the course of 4 to 2 days, after being exposed to exponentially increasing radiation, it only declines by like 55 megapascals. Next, we'll talk about aluminium. It is the most abundant metal on Earth, and it makes up more than 8% of the matter in the Earth's crust. Aluminium is a very reflective material. The reflective surfaces bounce the remaining energy out of the gaps at the sun shield layer's edges, which is why NASA chose this material as a coating. The next material I wanted to touch on is silicon, which is a non-metallic chemical element in the carbon family of the periodic table. Silicon makes up 27.7% of the Earth's crust and is the second most abundant element in the crust, right after oxygen. The next process I wanted to touch on is doping. So doping is an example of diffusion, and diffusion, as we all know, is the process through which atoms, ions, or molecules in a material move from regions of high concentration to regions of lower concentration, and doping helps to strengthen the material by introducing an impurity. So there are many different reasons why NASA probably decided to go with doped silicon. Doped silicon increases electrical conductivity, and silicon also has a high emissivity. This means that it emits heat and light and blocks out the sun's heat from reaching the instruments on the telescope. As we mentioned earlier, those instruments are very precise and sensitive, so them picking up the shield's own heat would basically work against it. So the coating needs to be electrically conductive so that the membranes are electrically grounded to the rest of the telescope and do not build up static electric charge across their surface. Thanks everybody for listening. I hope you guys came to appreciate these types of engineering accomplishments, and I hope you guys saw the application of our material science class in the real world. Thank you.